in Tokyo, in Taipei, in Shanghai, and in Santiago de Chile. And I'm proud of Europe. I'm proud of Europe because we have invested so much in this project. We have put altogether more than 44 million euros because we can be proud that Europe has a winning formula. And that winning formula is simple. We believe deeply in the freedom of science. We believe that scientists are the ones to make the choices, that the choices of science are not done by politicians. We believe somehow in the intuition of science. Stephen Hawking once said something that I would like to finish these words today with you, with this excitement of us. He said, "It is said that facts are sometimes stranger than fiction, and nowhere this is more true than in the case of black holes. Black holes are stranger than anything dreamed up by science fiction writers, but they are firmly matters of science fact." So, ladies and gentlemen, I think that I have not been this excited since when I came in 2014. If there's a big moment for all of us, it is today. And so this big moment is shared with so many in the public, so many today here, and I want to invite all the team. And for that, Professor Heino Falke is here, so he will come immediately to my place and tell you, and we will join all of us here in the room, we will join him unveiling the image. So Professor, please come and I'll go.
Still have to thank you. Now I have to fill the time actually until we're allowed to actually, start the unveiling sequence. I thought I'd use the time to introduce our team here that's here today on stage. We have Monika Moshi-Brodska from Radboud University, working on theory and imaging of black holes. Luciano Rizzola from the Goethe University in Frankfurt. We have Eduardo Ros from the Max Planck Institute for Radio Astronomy, and we have Anton Census, the director of the Max Planck Institute for Radio Astronomy in Bonn, and also chair of the board of the Event Horizon Telescope. And we have, a lot of team members here in the front row. Michael Kramer was already mentioned, our co-PI. You have Remo Tilanos, the project manager of the Event Horizon Telescope. Glad you're here with us today. Colin Wonsdale, who is the co-chair of the Event Horizon Telescope project. And now we have to start with the session. We are looking into space, towards a galaxy, a giant galaxy, 500 billion light years away from us. Sorry, 500 billion kilometers away from us. Very big galaxy which was suspected to host a supermassive black hole in the very center. 101 years ago, someone discovered a streak of light, which is plasma shooting out of the center of the Milky Way, marking the supermassive black hole. I never believed that this black hole was as big as people said, until we saw that. This is the nucleus of the galaxy M87, and this is the first ever image of a black hole.
This is the first image of a black hole.
C'est la première image d'un trou noir. What you're seeing here is the result of many people working together. You have probably seen many images of black holes before, but they were all simulations or animations. And this is so precious to all of us, because this one is finally real. What you're looking at actually looks like a ring of fire. And it's actually created by the force of gravity, by the deformation of space-time, where light actually goes around a black hole, almost in a circle. And that creates that circle that we see here. It has a diameter of, I forgot the number actually. 100, no, it's 100 billion kilometers. Now I got it right. It has 100 billion kilometers. But actually, at the distance, at a huge distance of M87, it actually will appear as a mustard seed in Washington, D.C., as seen here from Brussels. The size of the ring is actually determined by the mass of the black hole, and very independent of all the parameters of the black hole, the modeling. And so we can derive from that size directly what the mass is. And it's 6.5 billion times the mass of the sun. That is an enormous black hole that we see there. We see also more in there. We see this dark region in the middle. I've always been asked by my colleagues, or told by my colleagues, you cannot see a black hole, can you? And I think they're right. You cannot see a black hole, but you can actually see its shadow. And that's when the light actually disappears behind the event horizon, creating that dark region, that dark shadow we see there. And this is amazing if you think about it, where if you know the story behind that image, we're looking at a region that we've never looked at before, a region we cannot really imagine being there. It feels like really looking at the gates of hell, at the end of space and time. The event horizon, the point of no return. That is awe-inspiring to me at least, but it's also important for physics. I think my colleague Luciano Rezzolla will now continue and explain to us why this is so important.
Questa è la prima immagine di un buco nero. So, black holes are part of our daily knowledge. In fact, even a child knows what a black hole is, and the best definition I've received actually comes from a child who simply said, well, it's just a hole you cannot fill. So they're very simple, but they're actually extremely problematic in physics, and because of the properties they have. The first property is that at their center, in a single point, we think the laws of physics break down. We call this point a singularity. Another property is that this singularity is covered by a surface, a mathematical surface, which is called the event horizon. Gravity is so strong on this surface that nothing, not even light, can leave it. And this surface separates the interior from the exterior, and nothing from the interior can leave and be transmitted to the exterior. And for a scientist, this is a drama, because scientists want to know everything about every corner of the universe. So having a region where you say you cannot experiment there, or you can experiment there, but you cannot tell the results of the experiment, is extremely frustrating and puzzling. And the same puzzling thought was shared by Einstein. So how do you get to terms, you come to terms with this idea? Well, the first thing you want to do is convince yourself that black holes exist, and in particular an event horizon exists. And the image we have produced does exactly that. So you may wonder, how do you know it is a black hole? And it is because it matches extremely well with the prediction that we can do from theory. And this is shown in this picture over here. So on the left, there is the observed image. On the right, there is a theoretical prediction. And as you can see, the analogy is remarkable. As a matter of fact, we have carried out over these last 6 months the most extensive investigation of what happens to plasma, to matter, as it falls onto a black hole. We have used supercomputers and highly advanced numerical codes to calculate what happens. And what we've learned is that as matter falls onto the black hole, it will start rotating at speeds which are close to the speed of light, and will become hot and emit light, especially in the radio frequencies, which are the ones that our telescopes can capture. But these simulations are not sufficient. If you want to know what a black hole looks like as an image, you need to take into account that light doesn't move on straight line near a black hole. Just contrary to this room, light can come from all sorts of places. And so light can be bent, can be lensed, and so the image that you obtain by looking at a black hole can be very counterintuitive. And we have carried out a very extensive investigation. We built tens of thousands of synthetic images which cover all the possibilities that we think are realistic conditions under which a black hole is formed. And this is how we have come to conclude that this is a black hole as predicted by Einstein. Now, you may ask, what is the meaning of this discovery? For many of us, it has different meanings, but there is one meaning that we all share and is very precious to us. We have transformed a mathematical concept, that of the event horizon, something that I normally write on a blackboard when I lecture on this, into a physical object. Something that we can test, and we can measure, and we can observe repeatedly. And you may think this is a minor thing. Actually, this is a fundamental first step in any scientific progress. It's a scientific method. Be able to make an experiment and deduce from this what are the, how does nature work. And now I'll leave the word to my colleague Eduardo Ros to explain how this beautiful experiment was first carried out.